but not so fast. Before a star settles into middle age on the main sequence, it has to shake off some of its youthful energy. In particular, more technically, what's going on is that the end of collapse is accompanied by these polar outflows that we saw in the case of L1527, and even more directly collimated high-velocity jets of material being ejected from the poles of the star, so along the axis of its rotation. It turns out that these fulfill a very important part in the mechanism of collapse of stellar formation itself, because they carry off excess angular momentum, allowing material to accrete onto the star from the protoplanetary disk. The exact mechanism that governs their creation is still being nailed down, but we can observe them. We can observe them because this ejected material plows at high speed into the surrounding gas, compressing it and heating it, and then, as a result, the material glows. These were first discovered and termed, these objects, these regions of hot glowing gas, were termed Herbig-Haro objects. I don't know how to pronounce either of those names correctly, but it was later discovered that they were associated with the formation of a star. So what were considered as two Herbig-Haro objects turned out in the middle to conceal a nascent star. These could be 50,000, 100,000 astronomical units away. It took a while to make sense of this. And we've been watching these objects for long enough now that we can actually produce sequential frame-a-year movies of their evolution. Here's the first Herbig-Haro object over 8 years, and you can see the jet expanding. Here's another film of another Herbig-Haro object, and what you see here is that there's a structure to this jet that's being ejected. It's not a smooth jet. There are these clumps. They're about the size of the solar system, to give you a scale, and these clumps are supposed to be expected to be regions where the ejecta from one rapid pulse are plowing into ejections from a previous pulse, which tells you that there is a structure to this ejecta, this process of ejection. It's not completely smooth. And what this causes in the vicinity of the star, of course, is these huge stellar winds that we talked about. Stars in this phase, or low-mass stars at this phase of their existence, are called T Tauri stars. They exhibit irregular and rapid variability, possibly associated to changes in the opacity of the dust and clouds that still surround them. They exhibit huge rates of mass loss, as much as 100 millionth of a solar mass per year, and this phase can last for 10 million years. This is 1 million times the rate at which the sun is losing mass to the solar wind currently. So the sun, in its 10 million year T Tauri stage, lost a lot more mass than it will use throughout its entire 10 billion year main sequence career. And these winds are directed out from the poles, but when I say directed out from the poles, you need to get a scale. Notice that the scale of this internal cylinder is about 100 astronomical units, so that there is this outward flow in all directions, out into the disk, except at the very surface of the disk. The models, as I said, are not quite clear on how to model this. There used to be, the prevailing opinion was at some point that these waves are generated, this outflow is generated by the shock wave when the collapse stops and there's infalling matter colliding with it. Of course, as one would expect from the bipolar nature, it turns out that the stellar magnetic fields play an important role. These are very violent and dramatic events. You can see that here in this movie. That bubble is approximately 100 billion kilometers across, and it's dramatically growing. These other stellar types are the higher mass analogs of T Tauri stars. All star formation is accompanied by this violent outflow. This is what cleaned out the solar system. And now, having shaken that off, the sun is indeed ready to settle under the main.